this video lecture, we will be discussing the topic of radioactive decay. Radioactive decay is the spontaneous breakdown of an atomic nucleus, resulting in the release of energy and matter from the nucleus. The nucleus of an atom is composed of two particles, protons, which are positively charged, and neutrons, which have no net electric charge. The protons and neutrons that make up the nucleus of an atom are known as nucleons. There are three types of radioactive decay based on the type of particle that is being released from the nucleus: alpha decay, beta decay, and gamma decay, which we will discuss later in this presentation. For radioactive decay, we use the AZ notation, which is shown on the right side. The proton number of an element gives it its chemical properties, as well as the name of the element itself. The proton number of the element is denoted by the letter Z, and the number of nucleons, which is the number of protons and neutrons in the nucleus, is denoted by the letter A. The number of neutrons is denoted by the letter N, but we oftentimes don't write the value of N simply because if we know the proton number, we can therefore identify the corresponding element. In this case, the element has 6 protons. We can identify the element by looking at the periodic table and searching for the element that has 6 protons, which is carbon in this case. It is important to note the relationship between these three values. The nucleon number A, which is also known as the atomic weight of an element, is equal to the number of protons, Z, plus the number of neutrons, N, to get the equation A equals N plus C. So let's apply this equation to a practice problem. Say that you are given the values A equals 144 and N is equal to 74, and you are trying to find the value of Z, the proton number. All you have to do is rearrange the equation to solve for Z. Then you plug in your known values, which are A and N, and calculate that Z is equal to 70. The first type of radioactive decay we are going to discuss is alpha decay. In alpha decay, an alpha particle is being released from the nucleus. This alpha particle consists of 2 protons and 2 neutrons. As we discussed previously, an element is defined by the number of protons it possesses. If you take a look at the periodic table of elements, you can see that helium has 2 protons. So we now know that the alpha particle that is being emitted is helium. There is a simple equation that we can use to demonstrate how the alpha decay reaction works. Remember that A is equal to the nucleon number, while Z is equal to the proton number. The X on the left side of the reaction signifies the parent nucleus. The Y on the right side of the equation represents the daughter nucleus that is being formed. Also remember that an alpha particle is emitted during an alpha decay. In order to figure out the daughter nuclei that is being formed, all you have to do is look at the nucleon number of the parent nuclei, A, and subtract 4 from that number. This is because the alpha particle is already contributing 4 nucleons. Next, you look at the number of protons, Z, that the parent molecule has and subtract 2 from that number, due to the fact that the alpha particle is already contributing 2 protons. Once you get the proton number, you simply just refer to the periodic table and search for the element that has the same corresponding proton number. The next type of radioactive decay is beta decay. There are 2 types of beta decay: beta plus decay and beta minus decay. In beta minus decay, a neutron is being converted to a proton. In this type of decay, an electron is being emitted. The general reaction for beta minus decay is shown below. Similarly with the alpha decay reaction, X stands for the parent nucleus, and Y stands for the daughter nucleus. A is the nucleon number, and Z is the proton number. Notice in this equation, though, that there are two new parts. The electron that is being emitted is shown to the right of the daughter nuclei. In addition, there is an antineutrino added to the equation. This is needed in order to conserve energy and momentum, since the antineutrino has no charge. To find the daughter nuclei, you must add one proton to the proton number of the parent nuclei. The nucleon number stays the same. Finally, you once again refer back to the periodic table to determine which element corresponds to what proton number. For a beta plus decay reaction, a positron is being emitted, meaning that a proton is being converted to a neutron. The positron has the same mass as the electron and is numerically the same, but with a positive charge instead. Taking this into consideration, the daughter nucleus will have one less proton than the parent nuclei, and we will have the same nucleon number. In addition, a neutrino is added in order to conserve energy and momentum. The final type of decay is gamma decay. It involves a high energy photon, known as a gamma, being released from the nucleus. In gamma decay, a parent nucleus starts out in the excited state, but then falls back to a lower energy state. This high energy state is denoted by using an asterisk next to the parent nuclei. For this type of radioactive decay, the proton number and therefore element remain the same. The only addition is the high energy photon that is being emitted. Now let's apply this knowledge to some practice problems. The question below asks us to complete the following radioactive decay formulas. For the first problem, we must identify what type of decay is being shown. We notice on the right side of the arrow that there is an alpha particle being emitted, so we can classify this as an alpha decay problem. With knowing this, all we have to do is A minus 4, which is 212 minus 4, which is 208. And then we have to do Z minus 2 to figure out the proton number, which is 83 minus 2, which is 81. Now that we know the proton number is 81, we can refer to the periodic table and see that thallium, which is Ti or TL for short, is the unknown element of the daughter nuclei. For the second problem, we again have to first determine the type of decay. We see that an electron is being emitted, so we know that this is a beta minus decay. Knowing this, we must add a proton to the parent nucleus, so Z will equal 37. And we know that the nucleon number will stay the same, so A equals 95. We once again refer back to the periodic table and determine that rubidium, which has an element symbol of Rb, is the daughter nucleus. For the third problem, we know that it is an alpha decay because there is an alpha decay particle present. So unlike the first problem, we must do A equals 140 plus 4, which equals 144. Next, we must do Z equals 58 plus 2, which equals 60. If we look at the periodic table of elements, we see that neodymium, Nd, is the parent nucleus. The fourth problem is another example of a beta minus decay problem, since there is an electron being emitted. Again, we just add one proton to the parent nucleus proton, to get the proton number of the daughter nuclei. The nucleon number remains the same. We determined that the proton number is 6, which corresponds to carbon. The fifth problem does not show any electrons, positrons, or alpha particles being emitted. So we must look at what is given to us. We know the identity of the daughter nucleus, as well as the identity of the parent nucleus. To find what particle is being emitted, we do 234 minus 230, which equals 4 for A. Then we do 90 minus 88, which equals 2 for the proton number. Looking at the periodic table once more, we know that this matches up with the alpha particle, helium. So we know that this is now an alpha decay problem. The fifth problem does not provide us with the parent molecule, but gives us the daughter nuclei and shows that an electron is being emitted, so we could classify it as a beta minus decay. We simply just subtract 1 from the daughter nuclei proton number to get the proton number of the parent nucleus, which is 6. And as we know in a beta minus decay reaction, A stays the same. We find once more that the element that has 6 protons is carbon. So, knowing all of this information, the answers in blue are our final answers for all of the problems.